if you are taking that exam tonight. It's kind of a shame that it happened on this day, because we've got a really cool topic today. Right? We're getting started with waves in today's lecture. So what I'll try and do for those of you who are writing calc, I'll try and finish just a little tad early today so you can go and get prepped with that. But yeah, so let's get into this topic of waves, which is an important topic, not just in this course, but in physics and engineering. It's actually one of the most historically important types of things we can model. Now, we started the course talking about oscillations, right? We had stuff going back and forth indefinitely that we could represent with some equation of motion. Waves are actually very similar motion. A wave is basically a traveling oscillation. If you take a point on a wave, it's going up and down as it moves in one direction. So you can imagine, as I move here and oscillate my hand, you would trace out the path of a wave going across the front of the class here. So waves and oscillations, they're modeled very similarly, which is why they're always taught in the same course typically. Say, okay, here's the oscillation stuff, now let's get a bit more complicated and study waves. So it's mechanical motion, similar to our oscillations unit that we're going to be talking about. Now, the big difference is the fact that we're traveling in space. Remember, the ideal spring, for example, just went back and forth, basically at the same spot forever. Waves, they travel and move through space. So they're moving with both space and time. Now, what we'll see today is, if we have some wave on a string, like maybe in high school you did the thing where you grab a rope, and your friend grabs a rope, and you do this to make a wave, right? We're going to talk a lot about that type of wave today, the wave on a rope or string, and how we can represent it mathematically. If you were to look at any point on the wave on a string, it's going up and down in simple harmonic motion. So in fact, when we have a periodic wave on a string, any one point on the string is going up and down, just like we talked about before. We'll see why that is here today. Okay, so we're going to talk about some of the major wave types, these mechanical waves, today. So mechanical waves are stuff that travels through some medium. So it could be on a string, could be in water, could be in air. You need something for the wave to travel in. So for the most part today we'll talk about waves on a string, but it's just any medium that the wave is traveling in. So there's three types. There's transverse, longitudinal, and some combination of both. So what I'm going to do, we're going to go through some diagrams that will talk about this. But basically a wave on a string is something we call a transverse wave. You can have waves in a fluid longitudinally that we'll see, and you can have some combination. Let's look at some pictures to make sense of these. Oh, here's all three of them at once. So we'll start with this top diagram here. You take your band and you make a wave on a string. The string is going up and down, but the wave is moving this way. If the motion of the material is perpendicular to the motion of the wave, we call that a transverse wave. So we see here on this diagram, the actual string particles are going up and down, but the velocity of the wave is this way. They're perpendicular, aka transverse waves. We can also make longitudinal waves. So imagine we have like a vial or piston or something here with some water filled in this container. And we can oscillate this piston, which would oscillate the water in here. In this case, the particles in the fluid are oscillating in the same direction as the moving wave. So you see here these little water molecules, for example, they're moving back and forth in the same direction that the wave is going. Finally, you can have some complicated combination of both of these. such as waves on a liquid. So you have some liquid here, the wave is moving in this direction, you have both transverse and longitudinal behavior. So you can have these three types. We're really just going to talk about type A. We're not going to do the math for either of these here in this lecture. Oh, a daily gift. Nice. It's a bit less enthusiasm than usual, right, with our small crowd here, but we're a little pumped up, right? A little pumped up for some gifts here. So let's take a peek at some gifts. So let's say we have a string. We can have different types of waves. You can have a pulse, like a single pulse on the string, or you can have standing waves where they're oscillating back and forth. You can have traveling waves where the whole thing's moving. So just on a string alone, you can have a lot of different types of wave behavior. We're mainly going to talk about something called periodic waves here today. This is a good one. Let's say we had a slinky. Has ever played with a slinky before? Yeah, they're pretty sweet. My daughters play with them. They mainly just break them. It's real rattling. When you tangle a slinky, it's so hard to untangle, and then it's just never the same. So anyway, I keep having to get new slinkies. But the basic idea is you have transverse waves where the wave is kind of this way, but it's moving this way, and longitudinal where the wave is moving in the same direction as the direction of the wave. So transverse, this whole thing is moving this way, but the waves are up and down this way. Longitudinal is all within that medium itself. And we could also have the combination of both there. So anyway, that's a couple of gifts there. Let's get back to going through stuff. So the transverse ones, as I said, basically we move perpendicular to the motion. Like if the string is oscillating this way, the wave is moving this way, those two things are perpendicular. That's the main focus of this class. So let's say the y direction is up and down in the classroom, and the x direction is this way and this way. Well, transverse waves, we can have the string going up and down in y and moving in x, for example, and that's what we'll talk about here today. Really quickly, we'll say the ones we aren't going to do today, like longitudinal waves in a fluid. The fluid, the particles, move parallel to the direction of the wave. So for longitudinal waves, our wave is moving this way, our particles are also oscillating this way. Everything's kind of parallel or on the same line. And then finally, combination of both. This is super complicated. Absolutely, I'm not going to ask you to do anything like this, but you would have some combination of both of those. You'd have some transverse direction, some longitudinal. It's like complicated water waves on coming up to a beach or something you can think about. And there's people who study this. We actually have a physicist in the physics department here who studies fluids and waves and stuff like that. So it's an active area of research. It's not fully understood in general, wave behavior. So periodic waves, this is the one that we're mainly going to consider in this course, especially in this lecture. We're going to talk about some periodic traveling wave. You could think about it like a sine or cos function, something that is traveling in a nice, perfect, periodic wave pattern. And that's what we're going to study because that'll just make things easier. As we'll see, we're going to have an equation of motion and solution. It's kind of nice when our solution is cosine or sine. Kind of looks like a wave. That's why we do this like this. So how can we make the wave? Well, let's bring our favorite ideal spring into the picture. So we have some ideal spring here that's oscillating back and forth forever, attached to a string. If you connect this ideal spring to the string, it will make a perfect periodic wave. This is why at every point here, if you look at one particle on the string, it's just going up and down in simple harmonic motion. So we can use our simple harmonic motion to generate a perfect periodic wave with some amplitude, some wavelengths. We'll talk about all that here today. how we're going to generate our wave on a string. We could also do this for the longitudinal case. We're not going to, but in theory you can model this, where you have some piston here, going back and forth, causing the water to have more dense regions, less dense regions, and this travels as a periodic wave as well. You could just think kind of constantly pressing the water, and it creates some longitudinal wave in the water. You don't see it the same, but it'd be like a difference in the density of the water that's traveling. Oh, a daily double GIF. Okay, so again, I figured you know the whole daily double thing, should probably mix that in once this semester. So we're going to do a second GIF today, because it's a nice way to visualize some of this stuff. So if we look at our wave on a string, it's going to be some perfect sine or cosine function. But if you're up here and you're making that wave on a string, what's happening is each point on the string is just going up and down at the same location. It's not like your string magically takes off and you're chasing after it, trying to catch up to it. Every single point on your string is going up and down periodically, indefinitely, in simple harmonic motion. So if you look at any one point, like let's say we had a wave across the front of the class, we picked a point right here, we would see that point on the string just going up and down in simple harmonic motion. That's what that red dot's showing us. Finally, here's another nice one. Now let's treat the string, let's break it up into point masses. So we say our string is a series of a bunch of point masses. We can see here, every single point mass is going up and down in simple harmonic motion. So a traveling wave on a string is a bunch of point masses going up and down forever, and then we get this cool traveling wave pattern on the string. So this is how it's all connected there. Anyway, so let's get back to it. That wave we're making, it travels with a speed. What is that speed? It's lambda, the wavelength, times f, the frequency. So the wavelength would be like from one peak of the sine function to the next peak of the sine function. That would be one full wavelength of the wave. And the frequency is our frequency of oscillation, which is 1 over the period. So basically we have a wave, we can directly calculate the speed of our wave. There's other ways, we'll do that later, yeah. Yes, lambda, it's called the wavelength. It's basically how long is one full cycle of our periodic wave. So if you picture like the sine function, it goes like this, and then that's one full wavelength. I have a diagram later that will show exactly what the wavelength is. Okay, so this is a big moment here. Can't get too rapid, we don't have too much of us here, right? But it's still a big moment for us. We'll call it a nice moment regardless, which is we get to introduce one of the most famous equations in physics and engineering, known as the wave equation. Okay, so the wave equation is extremely important historical equation in basically modeling observed phenomena. The wave equation is how we make it is the equation of motion for waves. So it's the equation of motion, just like we had an equation of motion describing the ideal spring, this one's going to describe waves. It's not just waves on the string like we're talking about here today. We can make an electromagnetic wave equation where the solution describes electromagnetic waves. So the wave equation is very important. We're going to get to electromagnetic waves in a few lectures, but we're starting here with this 1D wave equation. So the wave equation in 1D, which is traveling in one spatial dimension, is this equation here. Two position derivatives of y equals 1 over the speed of the wave squared times 2 time derivatives of y. Now remember, we introduced these things earlier in the course. Those curly symbol derivatives. This curly d here is something we call a partial derivative. It's the exact same derivative rule from your calculus class. So the rule has not changed. The reason we use the different symbol is because now in the wave equation, our function has two inputs, right? We call this a multivariable function. So we have two inputs, x and t here. Therefore, when we take a derivative, unlike in the past, if you just have one input, it's obvious what you're taking the derivative with respect to. Here we have to specify which one of x and t are we taking the derivative of. So the wave equation is relating two x derivatives of this function to two t derivatives of this function. What is that function? It's the wave function. This thing's so famous that its solution has a name. The solution is known as the wave function, which is the function that satisfies the wave equation. If you plug this into the wave equation on both sides, you will get left-hand side equals right-hand side forever, just like we did for the ideal spring model. So it's very similar here. We have a cos function. We can plug it into both sides. It will always be equal. Okay? Now, this intuitively will look something like a wave, right? Some cosine function. This minus sign here tells us which way the wave is traveling. So if we're traveling in the positive x direction, we have a negative sign here in front of omega t. If we were traveling in the negative x direction, let's say the opposite way across the classroom, we would need a positive sign here in the wave function. Now, this kappa here and omega will define here shortly. But basically, this amplitude is the height of our wave that's traveling, just like the amplitude of our oscillations for simple harmonic motion. Okay, here's those parameters I was talking about. So kappa, that's what we call the wave number. So it's basically a measurement of the wavelength. It's 2 pi over lambda. Why do we do this? Well, cosine has to have inputs of radians. So to convert what you have in your argument to radians, you multiply x by 2 pi over lambda. Dimensionally, you have radians per meter times meter. Meters cancel, you have a radian input to your cosine function. So we define this thing called the wave number. It's 2 pi divided by the wavelength of the wave. Omega, same thing as before, angular frequency, 2 pi times the frequency. These two things can be related by the velocity. So omega equals Vk is a way we can relate the angular frequency, velocity, and wave number of our wave. We'll talk about where this comes from here in a slide or two. But anyway, these are all kind of foundational relationships in wave theory. Oh, so here's what you're asking about before, about the wavelength here. Basically, the wavelength of a wave is if we were to plot y versus x, how long is one full cycle here? That's what we call the wavelength. You have to be careful here. We can plot y versus x or y versus t, right? This is a multivariable function. So this would be like at one fixed instant in time. What is y versus x? This is how far this wavelength is. Over time, this thing would be traveling. So this is like a plot of our position versus position, like we have at the front of class here. We can also plot y versus t. So here's y versus t, where one full cycle would be what we call the period. So this would be like if we fix the position, like right here, let's say, how does y change as a function of time? And it's just simple harmonic motion. This is basically the ideal spring problem. Okay, so when we plot a wave function, we can plot y versus x or t, or we could plot all at once in 3D. We could plot y versus x and t and see how this thing is moving as a function of x and t. But anyway, so this is the wave function here, describes a wave. So this relationship we talked about is sometimes called the phase velocity. We'll see why on the next slide, I believe. But basically we can relate omega, v, and kappa rearrange, and we can figure out that the velocity of our wave is omega over kappa, sometimes referred to as the phase velocity of our wave. And we just have to divide the parameters in our wave function, this omega and kappa, to get v. All right, so I'm gonna explain here why we call this the phase velocity. Well, it's because this cosine, the argument is sometimes referred to as the phase or just the argument. But basically, if we wanted to see how fast is a wave traveling, well, we can pick a point on the cos function and follow it and see how fast it's going. To have a common fixed point of the cos function, like the maximum 1, we need this argument to be a constant. So if this argument is a constant here, kappa x minus omega t plus phi equals a constant, we can take the time derivative of both sides. So ddt of x gives us v, ddt of t gives us 1, ddt of a constant gives us 0, ddt of a constant gives us 0. We're left with this relationship here, taking the time derivative of both sides, which we can rearrange, which gives us the velocity. Right? So it's found from the phase for a cosine function here, and basically this is how fast our wave is traveling in some direction. All right. Now, we're not really gonna determine where this wave equation comes from. There's a way you can do it using Newtonian forces and stuff and figure out the equation of motion using Newton's second law. It's a bit complicated for a first year course, I decided, so I'm not gonna go through it, but there's a simpler, much simpler way we can figure out why this thing works. And that's based on our wave function here. We know we have some cosine function, and at each point, the particles are going up and down on the string with some velocity and acceleration. So we can figure out what's the velocity and acceleration of these points at any point by taking time derivatives, just like we did before, to find velocity and acceleration. So we can start from our wave function here and say, okay, velocity is 1 time derivative, acceleration is 2 time derivatives. Let's figure out what this acceleration is. So when we take 2 time derivatives of this wave function, we get this expression here, where we get the cosine back. Remember, you take the derivative of cos, you get sine, one where you get cos. So you get something in terms of cos. You can write the acceleration, which is 2 time derivatives, as negative omega squared times that same function, which is just a simple harmonic motion ideal spring type of equation. Right? So this tells us that this equation here determines one point going up and down forever. It's just a simple harmonic motion equation. So that's from taking 2 time derivatives of our wave function. What about 2 x derivatives? This is actually a very calculus topic, so hopefully it will help today, or maybe you just don't want to hear any more about calculus right now. But remember, if you want to find if there's a max or min of a function, you take the derivative and set it equal to 0. If you want to figure out information about the curvature, concave up, concave down, you take the second derivative. So the second derivative of a function is the measurement of the curvature of that function. So we can find the curvature in our string by taking 2 x derivatives. We take 2 x derivatives, we get 2 x derivatives is negative kappa squared times that function. So in a nutshell, this function and this function is the same thing. We can set those equal to each other and see what we get. So let's set y equal to each other in these 2 equations. We set y equal to each other from the 2 equations, and we get the wave equation exactly as, this is kind of the opposite way of doing what we talked about before. You have this function, you know what 2 x derivatives is, you know what 2 t derivatives is, those are related to one another, that's what the wave equation is. It's relating the curvature of the string to the oscillation of the string, and that perfectly predicts all the possible motion. So anyway, that's one way we can find it. I won't make you do the more complicated ways. So anyway, here we have the wave equation. This tells us information about our traveling wave. So this wave is going up and down in y and traveling in x. The solution is the wave function. We can plug in y to both sides of this equation. This relationship always has to be true. So this wave equation tells us for a periodic wave on a string, this will model all the wave, and this is a function that represents the periodic wave specifically. So this is like modeling all waves on the string. This is the one we are talking about here today. What about if we were to do this in a different direction? What if we had a string hanging from the ceiling and it was oscillating towards and away from you in the z direction? Well then, we could still make a wave equation where z would be our function, that's the direction of oscillation, y is the direction of travel, up and down. So for the wave equation, the stuff in the bottom here, t and y, that's what are you traveling in? And then z, the thing that we're taking the derivatives of, that's what's the changing thing, what's the oscillating thing. So the wave equation, this one, when it's a traveling wave, we are oscillating in the function, we are moving in the input variable here. So you're always traveling in the direction you have here in the argument of the function. What about those signs? I want to go back to those signs there, because I said before, you could have a plus or a minus here, right? So let's say this is the positive x direction like usual, this is the negative x direction. If we're going in the positive x direction, we would have the negative sign there. If we're going in the negative x direction, we would have the positive sign there. Okay? So basically, why is this? The negative omega t phase will shift our cosine slightly to the right. So if you have a negative here, you slightly shift the cosine function to the right, which is in the positive x direction. So as you increase time, this function will visually be moving in the positive x direction as we increase time in our function. Okay, I want to reiterate, this function is a solution to the equation of motion, that is the wave equation. So if we plug in our wave function into both sides of the wave equation, we get left-hand side equals right-hand side forever, just like we got with the ideal spring. So you take two x derivatives on this side, two t derivatives on this side, you will always get these two are equal, therefore it satisfies that equation of motion. All right. So as promised, I'm on track to finish fairly early here, so you can get back to your calculus study. What time's the exam, by the way?
7.
7 o'clock. I'd recommend take a bit of a brain break after this, right? Get a bit of rest, get some food in you, right? You want to be able to think during the exam, right? It's a difficult subject, so anyway, that's my advice for the exam here. Don't just go and start cramming and be too worn out by the time you get to the exam. All right, so the final topics we're going to talk about today, stuff like frequency still exists. Frequency is one of the periods, same as before. We have this new expression for omega, so omega is Vk, which is still 2 pi f, and we can replace kappa with the wavelength expression, we get a different expression. We can replace f with 1 over t, get a different expression. So there's a bunch of different expressions for different wave parameters we could use if we wanted to calculate something. Like, hey, what's the wavelength of that wave based on this speed and frequency or something like that. So you can calculate the properties of a wave based on how these parameters relate to one another. Final topic topic of today's lecture is about energy in wave motion. So I'll just go over it fairly quickly. If you have more questions about it, you can come up and we can chat about it. But basically, if we have a wave that's traveling, it's carrying energy with it. So waves can carry energy. So we're often interested in what's the rate of energy transfer, which is sometimes referred to as the power, right? That's the rate of energy transfer. It's in units watts, which is like joules per second. So it's a rate of energy change. And basically, this is the function. I'm not going to make you find it. The only thing I want to note here, well, mu is the density of the string, but T is the tension. This is not the period here in the power relationship. I know it's annoying when physicists do that, but basically T here is the, what do you call it? T here is the tension in the string. So this is what tells us how the energy is transported as a function of time. So if we plot power versus time here, it's a sine squared function. As our wave travels, if you pick a particular point and see how much energy is at this point in time, it's increasing and decreasing as a function of time according to our sine squared function. Okay, so when the sine function is the maximum, we have maximum power. Even at minimum, this is squared here. So anyway, you have this power increasing, decreasing. If you're talking about like an engineering application, for example, typically you're more interested in this quantity, which is the average power. Right? That's the average power being transmitted over time. You don't care so much often about instances in time, like how much energy are we actually sending here? So we can figure what's our maximum power and what's our average power based on this function. So this function is the same as power like we talked about before in units watts. It's the energy transport per second at a given point in time on the string. So we often are interested in the maximum and average power. So that's the final two things we will talk about. How do we find them? Well, the maximum is super easy. When is the sine function at a maximum? When it is equal to 1. So sine squared is equal to 1 is when we have max power. So if you just set sine squared equal to 1, that's the maximum power we would have transported by our wave, which is given by this expression here. And then, as I said, often more interested in the average power, which is over time, on average, how much power are we transporting. And another reason why this is of super interest and importance, well, we're going to talk about electromagnetic waves, which also transport energy, like from the sun, for example. So you're often very interested in kind of the average power emission in cases like this. But remember, these equations here are for the string. These are for our string with some tension and stuff. So how do we do this? And we'll see this for EM waves as well. But you want to find the average of the sine squared function over one full cycle. So if you average the sine squared function over one full cycle, you get 1/2, exactly 1/2. So you can just take that sine squared average, plug 1/2 into the power function, you just replace sine squared with 1/2, and that's the average power over one full cycle. So each full cycle of the wave, this is how much power we're transporting. Anyway, as promised, let's wrap it up here so you can go focus on Pell. The final slide here is we could just take the velocity versus tension and density equation and just replace that equation with a couple of different variables just by using that equation and subbing it back in. You don't have to do it, it's just something